The single sample test for proportion is a great example of how we can use either p-values or critical values in a hypothesis test. Let's start with the oldest version of a test on proportion, Fisher's exact test, which is going to use p-values. A one-sided test looks like this. The null, the proportion is less than or equal to some null value, and the research hypothesis, the proportion is greater than some specified value. Now, to do this, we'll just calculate the p-value, and it's just the probability of seeing the number of successes or more under the null hypothesis. So that's where the pi 0 comes from. And so we'll just add up all those binomial probabilities from k out to n. That was a greater than. Now the other one-sided hypothesis, the research hypothesis says the proportion is less than some specified value. And so the p-value is even simpler. We'll just calculate all the sum of the probabilities from 0 up to the observed value k, add up all those binomial probabilities, and that'll give us the p-value. So let's look at some examples and see how this works. So Taylor has a coin which might be biased. She flips a coin 10 times, gets 9 heads. Does this suggest the coin's biased? Well, calculate the p-value, which is just the probabilities of seeing 9 or 10. So here's 9, here's 10. Those are the two probabilities. We add them up, and the p-value is 0.0107. This is strong evidence, so we'll reject the null. The coin appears to be biased. If you'd like to do this calculation using R, you can use the p-binom function in either of these two ways and get the calculation done without having to do any hand calculation of your own. How about for the other side? Taylor tries again. This time she flips a coin 12 times and gets 3 tails. Now again, we have a binomial sampling distribution, and we'll calculate the p-values, which just says calculate all the probabilities from 0 up to 3 using the null hypothesis. And this time we get a p-value of 0.0730. This is suggestive but weak evidence. We like alpha equals 0.05. So we do not reject the null at the 5% level. Again, we can use R to do this, and p-binom for 3 will give us the sum of those probabilities. Now, some people don't like adding up all those binomial probabilities, especially when the sample size gets to be very large. Turns out we can approximate the binomial with the Gaussian distribution. And the way we do this is to equate the means and variances or standard deviations. So the mean is just n times the proportion. The standard deviation is n times the proportion times its complement. Take the square root of the whole thing. This relationship was noted and exploited by Abraham de Moivre around the time of the American Revolution. So this is not exactly a new test. Here's his idea. The bars show a binomial distribution, the curve shows a normal distribution, and then what we're going to do is basically try to use normal probabilities to figure out, to equate to the binomial probability. Now, there is a problem here in that binomials values only occur at the integers 0, 1, 2, 3, 4, etc. Well, the normal is continuous and has all those values plus all the values in between. So when we do the matching, what we have to look at is where are we calculating the probability in the tails from? In this case, this tail goes not to the end of the bar, but to the middle of the bar. And so that difference is 0.5. And this is what's called a continuity correction. Okay. The basic idea here is that we can approximate the binomial probability for a given integer, x equals k, using the Gaussian by saying, well, the Gaussian probability is not just the probability of a point, but the probability within this entire bar. If that seems a little confusing, here's a table that shows you how to go ahead and make the continuity corrections for a variety of conditions, whether it's equality, strictly greater than, less than or equal to, strictly less than, greater than or equal to, or between. So let's use this approximation to do a one-sided test. We're going to test the claim of a large proportion at the 5% level. This is a z-test. So the 5% tail on the high side has a critical value of positive 1.645. Here's our research hypothesis. The proportion is greater than 0.8. And our sample data says in 200 observations, we get 170 successes. So let's do some calculations here. The mean, take the null value times the sample size, and the mean will be 160. The standard deviation, n pi naught, and its complement. Take the square of that product, we get 5.657. Now we can calculate a z-score. So the observed value, 170, minus 160. Continuity correction, because we have to move it down, because it's on the high side. Divide that by the standard deviation, and we get a z-score 1.679. Okay, this is greater than 1.645, so we'll reject the null hypothesis. Now, if you don't want to do all that calculation, you can fire up R and use prop test. You can see all the requisite numbers are there, and we specify the direction of the test. The one-sided test, of course, works in the other direction. We're going to look for a claim of a small proportion, again at the 5% level. So the critical value is 1.645, but this time it's negative. We're going to look at a very small proportion, 2%. That's our claim. Maybe that's coronavirus fatalities. And we'll look at a sample size of 1,500, and the number of events is 21. So the mean, again, n times the null proportion gives 30. The standard deviation, n times the null proportion times its complement. Take the square root, we get 5.422. And so now we'll go ahead and calculate the z-score. So the observed minus the mean, bring the bar forward this time to include the entire bar with a continuity correction. Add those up, divide by the standard deviation. And here's our z-score, minus 1.568. Okay. This is not less than minus 1.645. Do not reject the null. Again, we can use prop test in R with the successes, the sample size, the probability, and the less than alternative. What about a two-sided test? Let's do a two-sided test with no critical values, and so we'll just look at the p-value. We're going to claim that our proportion differs from 55% without any alpha specified. So the research hypothesis is the proportion's not 0.55 versus the alternative, what it is 0.55. Sample size of 3,200, and the number of successes is 1831. So the null mean, 1760, so that's our mu naught. Standard deviation, 3,200, 0.55 times 0.45, take the whole square root, we get 28.14. Calculate the z-score. Observed minus mean, and because this is on the high side, we're going to have to bring it down with a continuity correction. Divide by the standard deviation, we get a z-score of 2.505. Now, the p-value is kind of tricky, all right? We would look at the size of one tail using this z-score. However, it's a two-sided test, so there's two tails. So we have to multiply this probability by 2, and we end up with a p-value of 0.012, okay, which is very small. So strong evidence. And reject the null hypothesis. Nice.